All right, we're going to go after number 1 of 2024. So they give us a reaction of a monoprotic acid being titrated with sodium hydroxide, and you make sodium. Let's see, what acid is this? Sodium lactate and water. So they want to know in the structure A, circle the hydrogen that is the most readily precipitates or participates in the chemical reaction with the hydroxide. So again, all of these organic acids, so I'm going to just call this everything and then show you the carboxylic acid. In all of these situations, your acidic hydrogen is here, and that's because the electronegativity values of oxygen are pulling electrons away from that bond with hydrogen, making that hydrogen easily or more readily available to be ionized. Okay, that's a really long answer, but you would circle that hydrogen. B, student begins the experiment by by dissolving 10.22 grams of sodium hydroxide in enough water to produce half a liter or 500 milliliters. So let's get the molarity. Great. So this is 10.22 grams, and that's sodium hydroxide, so that's 1 mole. NaOH, so that's 40 grams, which turns out to be 10 over 4.25. Let me just do the math real quick. 10.22 divided by 40. So we got 0.2555 moles. Okay, and we will divide that by half a liter to get the molarity. So 0.511 molar sodium hydroxide. All right. Hopefully we're getting points here. Let's look at the next question. Sorry. Okay, they're giving us a graph. Good morning, Mr. Patterson. Part A, burette, 100 milliliters erlenmeyer, 25 milliliters. Here's the data. Okay, great. So C says, use the information in the graph to approximate the pKa. All right, since this is a weak acid, we know the pH, pKa, Henderson-Hasselbalch type thing, log A over HA. And this is a lot of notes for just this answer. The only way that we get to this point where these two are equal, because if they're equal, then the pH is the pKa, is if we titrate half of the acid. So in essence, you're taking half of the HA. So if there was 10, you're going to neutralize or pull off a hydrogen off of half of them, so you'll make 5 of those. So you would maybe have 10, but get rid of 5 by producing 5 of those. So in essence, we're going to the halfway point of neutralization. So that halfway point is going to be somewhere. If you look at the graph, it looks like the end point and equivalence point is at 16. So we need to be at a pH right about where it is on 8 milliliters. So that's just below 4. So you're going to say something like 3.9 for the pKa value. They will accept anything from like 3.7 up to 4.0. But again, where did it happen? It happened at the halfway to the neutralization point. So if it took 16 milliliters to neutralize, then the halfway point would be 8-ish, and then you want to guesstimate what the pH is there. Okay? So let's go on to D. Okay, D says, look at the diagrams. These all represent the relative amounts of species. water is excluded. And then it says A, or part 1, excuse me, draw an X on the preceding curve at a point where the titration mixture would be represented by the diagram. So in this situation, you have a diagram, and we know where the halfway neutralization point is, and the halfway was around 8 milliliters and pH of 3.9. But this, why am I saying this? Because this one is not at the halfway point. The diagram, if it was at the halfway point, you would have the same number of these as you would those, and we're not talking about the sodium ions. All right, they would be the same number, but they're saying you have 4 of these and 2. Okay, so you have more acid than you do have them that are being pulled apart. So you would be short of the halfway point. So you want to describe that that the X should be somewhere around 3 to 4 to 5. So 3 milliliters to, I don't know, you're not at the halfway point. So let's say 3 to 6 milliliter point. That's how you would go after that. Okay, was that D? Yeah, that was D1, part 2. Justify your answer. Oh, it's exactly what I say about the more particles. So there's more, if you will, HA than A minus, therefore less than 8. But close to half of that 8, so 4 I think was a fair, so you'd have to be around 4. Less than, you got to be less than 4, okay? But I think they're going to let you, no, you can't be less than 4. I'm saying it's less than 8, and around 4 would be reasonable because you have a 4 to 2 ratio, which means that 2/3 of the particles are there. So I hope that makes sense. Turned into some good verbiage versus what I just spewed out. Okay, let's take a look at the next question. So E, take a minute for me to flip this paper. E, okay, they do this experiment up above. One of them's already on the graph. So part 3, I'm sorry, it is not E. So part 3, and I'm not going to be able to draw this graph, that's for sure. The student represents, but uses a different solution, twice the concentration. Well, if this was the original graph, so I'm just going to sketch real quick, and I'm going to say the original graph like this, pretty long, okay? But now you're going to use twice the concentration of the sodium hydroxide. Then that means your graph is going to, like this was the halfway point before and here was 16, you're going to get neutralized in this range. So since it's twice, so you're going to look like this. Does it make sense? Good. Then you would have to make sure you label things well. I think they give you, yeah, they do. They give you a graph to write on. All right, E. In a third experiment, the student investigates the enthalpy of reaction. Man, it sounds like a Q equals MC delta T problem. Okay, student, 100 milliliters of the lactic acid solution at 20 degrees, 100 milliliters of the sodium hydroxide solution at 20 degrees in the calorimeter. The final temperature is 23.2. Assume that the density of each is approximately the same, so there's no loss in mass. And the specific capacity is 4.2, so it's basically water. Okay, so we're going to have a Q equals MC delta T. I like to spread these out. What you have here is you have your change in temperature from, I'm going to put some numbers down here. Your change in temperature is 3.2, right? 23.2 minus 20. The heat capacity, which we're putting here, is 4.2. And then the total mass, or the mass of the substance, is the 100 milliliters, but the density is 1 gram per milliliter, and then another 100, so this is going to be 200 grams. So all your units, okay, this is joules over grams C, and this is C. When you do this math, this turns out to be 2700 joules. All right? Let's see. E. All right, good. We calculated joules. Oh, it's over here. I'm sorry, I got these long papers. Okay, so part 2. I didn't know there was a part 2. I thought maybe it would be F. Anyway, so that's part 1. And part 2. Yep, of course. They want to know the molar heat capacity. Well, we have this many joules, which is the same as saying 2.7 kilojoules. Now, since this was an exothermic reaction, we got to be careful down here for the heat of reaction. This is how much heat energy was produced. But down here, we need to say negative 2.7 kilojoules, or we need to say that the energy was given off. That's really saying the same thing. But let's get our moles. Our moles is going to come from the fact that we had 0.1 liters. Now remember, molarity times volume, and the molarity was 0.5 molar, is going to be your moles. So this is 0.05. So if you take this number and divide by that 0.05 moles, and this was the moles of the substances involved here, this turns out to be negative 54 kilojoules per mole reaction. Now, let's say you didn't put this negative sign in, but at this point right here, you decide to say 54 kilojoules per mole released. Both of those will be correct. I hope that makes sense. All right, part 3. Okay, the student claims that if the heat is lost from the calorimeter due to the surroundings, okay, then the experimental value, so this 54, that we will be smaller than what it would have been. Yeah, we agree. If you're losing heat energy, so if this number that we just calculated, so we agree with this statement. Again, give an answer, then support it. So if you lost some energy to the surroundings, then this number that was calculated is less than the actual number from the reaction. So you want to say those things.